Okay, so good morning again. And any questions from the last week? No? Okay, so today your project 3 will be released. Project 2 has deadline today, submission deadline. So make sure you submit your work. And I will ask TAs to arrange a session, or actually they have their office hours, right? So you can go and their office hours, or you can contact them over email if you have any questions related to understanding of project 3. And if time permits, I'm not promising, but I will try to then explain it also in the next lecture. Okay. We are pretty much behind our tentative schedule now, because after getting your feedback, I tried to explain things on the board, which is slowing down me. So anyway, okay. So we are still continuing our discussion regarding scheduling of processes on a CPU. We have been covering the scheduling algorithms. I hope to get done with this scheduling algorithm for a single CPU. I hope to get done with this today. So until now, we are considering scheduling a single threaded process on a single CPU. And then after that, if we are done with that today, there are some minor issues related to thread scheduling. We will cover them, and then we will move on to the situation where we need to schedule multiple processes on a platform with multiple cores. Until now, we are still discussing a single core or a single processor system. Okay, and we have multiple processes to schedule on that single CPU. So last time, if you remember, we were talking about priority scheduling, and the basic idea was that if you have multiple processes, what you do is that you assign them priorities, and then you schedule those processes. If there are multiple ready processes in the queues, you schedule them based on their priorities. So the process with higher priority goes first, right? And then we said there are two different versions or variants. One is preemptive, one is non-preemptive. The basic difference is that if process A is already running on CPU with priority, let's say X, another process in the meantime becomes ready, process B, which has priority Y. Now, in the non-preemptive, what we do is that we let the process A complete its execution, and then we make another scheduling decision when the process A is done. But in the preemptive one, what we do is that as soon as the process B arrives, we check its priority. And if its priority is higher than the currently running process, we preempt the currently running process and let the process be execute, we schedule it for the execution. Okay. So shortest job first is both shortest job first and shortest remaining time first are the priority-based algorithm. The difference is that shortest job first is not non-preemptive, while shortest remaining time first is preemptive one. We then did an example. I'm not going through it again, right? So there were like two examples, one using non-preemptive scheduling, priority scheduling, and one using preemptive priority scheduling. We did the one with preemptive priority scheduling. The solutions are in the slides for both of them, and you can do them on your own and then compare your solutions with the one given in the slides. Okay, so we were talking about the priority scheduling, and okay. So remember we said, I actually asked this question last time, that what will be the issue with the priority scheduling if you have in your ready queue, if in your ready queue you have, let's say, 1,000 processes, and you need to make a scheduling decision. And all of these 1,000 processes have their own priority values, right? Or priority numbers. So what you need to do is that you need to scan the uh, whole list of the, or a whole FIFO of the ready queues. ready processes, right? So the issue is that, let's say if there is a process which has, let's say you have process 0 and it has priority of 0. Remember, we are using the convention where lower the number means higher the priority. And let's say that this process 0 has execution time of, let's say the burst of CPU burst of 1000 time units, right? Time units. And you have another process P1, which has the priority of 1, and doesn't matter, let's say it has any priority of X time units, right? So, and let's say you have another process 2, which is again has priority of 0, and it has some time units. Okay, first time. Now, what will happen, let's say, according to the priority algorithm, priority-based scheduling algorithm, you will first let this process execute, right? And once it is done, what you will do is that you will check the ready queue and find the process which has the highest priority, which is this one. So you will let this one execute, right? And let's say after that, once it is done, you again check and you find another process which has a priority 0. So basically, a situation can arise where the low priority process with the low priority will never get a chance to execute because the CPU is always occupied by the higher priority processes, right? So basically, which means that the lower priority process can basically starve or they never get the chance to run on the CPU. So actually, there is a rumor which is mentioned in your textbook that there was a case that in MIT back in maybe in 80s, they had a server system with multiple cores, having multiple processes running, and they were using the priority-based scheduling. So they submitted a process or a job for execution, and then eventually at some time they had to reboot their system, and then they found out that the process they submitted for execution 5 years ago had still not gotten the chance to run on the CPU because of the starvation. Okay, so I mean, definitely now the people have found the solution for this kind of problem, but this is the problem with your priority-based, the plain version of the priority-based scheduling. Okay, so how can we resolve this problem? Like, how can we make sure that a lower priority process, we can guarantee that it will ultimately get a chance to run and will not like starve forever?
Is there a way to create a hybrid between priority-based and just first come, first serve?
Yeah, but then first come, first serve is has its own issues. Like first come, first serve is also priority-based. I mean, the priority criteria is that if you arrive first, you get the higher priority, right? But the problem remains same there.
Yeah, what I'm saying is that, for example, if we have system calls or stuff like there's a call between the user clicked on this and there's another another process that we don't run and the system's gonna blow up. Like obviously that one is highest priority, but at some point after the one where the user click has been sitting on the queue for a minute, we give it priority. So we can increase the priority of everything that's in the queue based on how long they've been.
Okay. Yeah. So actually what he is saying is like, if there are processes or there are jobs which are waiting in the ready queue and waiting for a longer time, so what we can do is that we can increase their priority, right? And this is known as aging. The terminology for this in the context of operating system is aging. So what you do is like, so if your process P1 in our example is waiting for has been waiting for a certain amount of time, let's say you define a threshold, let's say it has been waiting for 10 milliseconds and it then never get a chance in 10 milliseconds to execute. And suppose it has, I'm further reducing its priority, let's say its priority was 10, not 0. Okay. So what you do is that you increase its priority by 1. So after every 10 milliseconds or after every threshold, we are defining the threshold to be 10 milliseconds. So what you do is that you change the priority of P1 from 10 to 9. And again, if next 10 milliseconds never gets the chance to run, you again increase this priority from 9 to 8, and so on. So ultimately, its priority will become zero. So when its priority will become zero, it will eventually will get the chance to run on the CPU. Okay. So this is the way one way how you can resolve the issue of aging, issue of starvation. Okay. Now, sorry. Now in the situation where you have, for example, even in our example, let's say we have two processes, P0 and P2, both having the same priority, right? Priority level. Okay, go ahead.
So here's the question about the change in priority. Once it runs the starving process, what happens with the priority status? Comes back to the original priority level, or it remains?
So in the case of aging, right?
Yeah, when it already run.
So to be honest, I don't know exact answer, but logically what I expect is that it goes back to its original priority level because aging was just a solution to avoid the starvation. So to be fair, it should go back to its original priority level. Maybe it doesn't need to do aging again on the second run, right? But I would expect logically to go to because that is fair, because that is what is its original and natural priority level. Okay, so here in our example, we have two processes, P0 and P2, both having the same priority levels, but they may have different burst times, right? Let's say this one has 1,000 time units of CPU burst, and this has only 10 time units. Now, if we allow, let's say, if the process P0 gets scheduled for the first, like we let it schedule first as compared to the P2, all the both of them have same. So now what will happen that it will be waiting for a longer amount of time as compared to this one, right? Because it has to complete the 1,000 time units, execute for 1,000 time unit, and then maybe the process 2 can be scheduled, right? So what you can do is that if you have two processes in a priority-based scheduling algorithm, if you have two processes with the same priority level, to avoid the shorter process, remember we talked about the conveyor effect. So here we basically you have the conveyor effect among the processes which have the same priority level but different burst times. So the smaller process gets stuck behind the larger process. So which means that your system becomes less responsive. So now what you can do is that you can use the round robin only between the processes, round robin policy only for scheduling the processes which have the same priority level. So basically what I'm saying is, let's say I have a round robin algorithm with quantum value of 5. So what I can do is that I can let it run for 5 time units, and then if there are other processes with the same priority level, I will allow P2 to run for the next 5 time units, and then P0 and then P2 and so on. So this will increase the responsiveness of the processes belonging to the same priority level. Okay. So here is an example how it is done. I mean, it is straightforward. Let's say you have 5 processes. The first number indicates the burst time. The second number in the brackets represents the priority level. So if we are using the priority-based scheduling algorithm, so we'll first look for the process with the lowest priority, which is 1. So process P4, it is scheduled for 0 to 7 because it is 7 burst time. Then once it is done, we look for the processes with the, again, highest priority level, which is P2 and P3. Both of them have same priority level and different burst times. So what we do is you can choose any one of them. Let's say you are selecting P2, and we are using now the round robin only to break the tie between the processes of the same level, priority level, and the time quantum is 2. So you let it P2 execute for 2 time unit, then switch with P3, then switch again with P2, because you are still at the system level, you are still doing the priority based, but to break the tie within for the processes of the same level, you are using round robin. So P2, P3, P2, P3, P2, P3. Once they all are done, then you move to the process with the next priority level, and so on. Any questions? Okay. So we have basically, I have mentioned this point that if you, let's say you have these 1,000 processes in the ready queue, and you want to select the one which has the highest priority, you need to scan the whole queue of the ready processes, which can become expensive depending upon the length of your queue. Maybe because you to find the one which has the smallest, you need to check the priority level of all of the processes. Maybe the one you get is at the head, but still you have to scan the whole to for the purpose of the comparison, because you never know where is the process with the highest priority, right? So it means that it can potentially become a performance bottleneck depending upon the length of the processes. And in real system, you have a large number of processes. It is not like our Y examples where we have only 4, 5, or 6 processes, but there are like hundreds and thousands of processes. So you need to like scan the whole queue. So how we can avoid this problem? You understand what the problem is, right? Scanning the whole queue and finding the process with the highest priority.
The organism processes priority in the ready queue.
Yeah.
If we use a heap, we have a n-log-n runtime on average for any new process.
Yeah, that is true, but still, I mean, if you can improve the search time, but still you will be searching, right? If it is not a linked list, depending upon the data structure. For example, if you use the tree, or you sort the linked list, then maybe you can improve, but still you need to do the searching, right? So one option is, definitely that is one option, but another option is that what your friend has said, that what you can do is that you can maintain, instead of maintaining one single ready queue, what you can do is you can maintain multiple ready queues, one for each priority level. So for example, in this case, like you have a ready queue for priority level 0. Then, so basically, which means that P0 and P2 will belong to this. Let's say I'm putting P0 here and P2 here. And you will have another queue and for another priority level, let's say priority level 1 and so on, depending upon how many priority levels are supported in your system, right? So you will have one priority queue for each. So what you need to do is that, let's say if you have a single core and you need to schedule the process based on the priority-based algorithm, what you need to do is that you first go and check if there is any process waiting in the ready queue of the process priority level 0. If there is a waiting process, sorry, not waiting, ready process. So you first schedule that. So you and you keep scheduling the processes. So you keep scheduling the processes from the highest priority queue first, and once it is empty, you move to the next one. And once it is empty, you move to the lower one and so on. Okay. So this is known as multi-level queue scheduling. So you have multiple queues, one for each priority level. And I have explained what is the motivation behind this. So what you can do, you partition the ready queue into separate multiple queues. For example, there is a more concrete example of where you can deploy this solution. Let's say you have two types of processes. One is foreground processes and one is background processes. So foreground processes are those which need to interact frequently with the user, or they need to display something on the screen or so on. And background are those which are, let's say, helping processes for the foreground, helper processes for the background process, foreground processes. Maybe they are generating some data. Okay. So what you can do is that you can prepare two different queues that you can put them into two different ready queues, one ready queue for the foreground processes and one for the background processes. Okay. So we are assuming that foreground processes have more priority as compared to the background processes for execution, because users have to interact with the foreground processes frequently. Not only that, so now let's say we have multiple queues. So one for the priority level 0, another for priority level 1. So remember here what we said, that we can use the round robin algorithm to break the tie between two processes belonging to the same priority level. But it is not like, you have to always use the round robin. Depending upon your requirement, what you can do is you can have a separate algorithm for each one of these queues. So basically, which means that as a whole on the system level, you are still using the priority-based algorithm, but to schedule all the ready processes belonging to the same priority queue, you can use any other scheduling algorithm. Let's say you can use round robin, or you can use a lot. What is this? You can use you can schedule the processor which is waiting for the longer time. Okay, so it depends upon your requirement. Any questions? Okay. So now there are like multiple facets of the same problem. So one is like you are still at the system level doing the priority level scheduling, but then at the level of the queue you can select any scheduling algorithm, and then you can also so remember we are still talking about a single core. You have, let's say, only core 0. Okay. So all these processes, they have to run on the single core, right? So you can either you can make sure that, as I said, all the processes from the priority level 0 are first scheduled or executed, and then only you move to the next level, and then only to move to the next level. This is known as strict priority. Or what you can do is that you can also do the time slicing, because the big issue is that if, let's say, there are like 100 ready processes in this queue, and there are 10 ready processes in this queue. Now, what will happen that they will have a very long waiting time, because this is over-occupied as compared to this one. This is relatively less occupied, right? So what happens that they will have a higher waiting time. So to reduce this, and basically they will become less responsive because they are not getting the chance to run on the CPU. So what you can do is that to avoid that problem, you can use the time slicing. You can allocate the time budget. Like, let's say you can say, okay, I will allocate 60% time to this one, and then maybe 30% to this one, and then maybe remaining 10% to this one. So basically, which means you are saying that if you have 100 time units, so first 60 will be used to schedule the processes which are waiting in the first level queue, next 30 for the processes in the level 1, and next 10 for the process in the level 2. Okay, so here is just an graphical depiction of the same thing what we have said already. So let's say you have multiple priority levels ranging from 0 to n. So for each level, you maintain a separate queue of the ready processes, and it is quite possible that queue at one particular level is more occupied as compared to the queues on the other levels. Like here, priority queue at the priority 0 is more occupied. So what you can do is that you can use RR or round robin to schedule the processes belonging to the same queue, or and to schedule among the queues, you can use different algorithms. For example, you can follow the strict priority ordering, which means all the processes in the higher levels must be completed before you move to the next level, or you can use the time slicing. So actually it is the same thing we have said, okay? So this is just another example where you have 4 different type of processes, and you then, based on the nature of those processes, you assign them priority. For example, real-time processes, they are given the highest priority because maybe they have some real-time deadlines which need to be met. Then system level processes which have next higher priority, and so on. And you have 4 separate type of queues. Okay. So we have talked about the case where you have like multiple queues, one for each type of priority level. But can you tell me something which I can consider as downside of this approach? focus on the board and think about the starvation problem and the solution we have for it, aging. In aging, what you do? If a process, let's say, is not getting the chance, you increase its priority after some threshold, right? But here we have separate queues for each priority level. So which basically mean that as you increase the priority of a process, let's say first it was at the priority level 7 and it didn't get the chance. So we increase its priority. So now its priority level becomes 6. So initially it was in the queue of the priority level 7. Now it need to be moved to the queue of the priority level 6. But this current design, the current approach we are talking about, it doesn't give you doesn't allow you to dynamically move the processes from one priority queue to another priority queue. Okay, so once a process enters in the queue, it stays in that queue until it gets the chance, right? So like this is only one case, like one criteria or one situation where we have to move around a process from one queue to another queue because its priority is changing, right? So there can be situations where we need to move around the processes from one queue to the other. And for that, this approach is not a suitable one. So that's why we have this slightly different approach, which is named as multi-level feedback queue. So where what you are basically doing is that you, based on some feedback, you allow processes to move around. Okay. So a process can move between the various queues. Aging can be implemented in this way. Aging is just a specific case where you can use this approach. So here, basically what you do is that, actually, let me first go to the next slide. So here what you do is that you have multiple queues. Let's say you have a queue at the top, then in the middle, and then at the bottom. So you use different type of priority level, right? So what you can do is, like, let's say you have Q0 in the next slide, and all the processes, so highest priority processes first go to Q0, the next priority processes, the Q2 and Q2 and so on. But for all the processes in the Q0, what you can do is that you can use the round robin algorithm, let's say, with quantum value of 8 milliseconds. And if you give a process the 8 millisecond to run belonging to that queue, if that process completes its execution, it doesn't need any more time, then fine, you are done with that. But if that process needs more time, like let's say CPU burst is not 8, but 24, so it cannot get completed in a one-time slice, right? So if you keep it in the same Q0, now what will happen? It will increase the context switching, right? Because it needs the 24. So larger the amount of time slices a particular process need to execute or complete its execution, it will incur more context switches, which mean more overhead, right? So as compared to like quantum size of 8, if I had quantum size of 16, now the same process with the CPU burst of 24 can complete in 2 slices, right? Incurring less number of context switches. So what you can do is that, you figure out that it doesn't get the chance to complete in 8 time seconds or 8 time units. So you move it to the next queue, which is lower priority queue. But the good thing is that it has higher quantum value of 16 time seconds. So but now you are basically getting 2 advantages. You have 0 and you have Q1. So the 2 advantages is that when I'm moving this process, let's say the process A, it first entered into this queue, but it didn't get completed in 8 time seconds. When I move it here, so now I will possibly incur the lesser number of context switches, right? One thing. Second, as compared to the case where I had not moved A from Q0 to Q1, if I had kept it in the Q0, I am now not, blocking the execution of those processes which can possibly complete it in 8 time units. Let's say here you had another process, B. and it could complete in now since it has moved, A has moved to the Q1, will get the chance. We will get earlier the chance. So as a whole, your system performance will increase. Okay. And so this is just a particular example of how you can use the multiple multiple level feedback queues for scheduling. And even like when you move the process from to the Q1, and in the Q1 you assign it to 60 milliseconds, let's say it gets completed, fine. If not, if it still needs more time, you can move it to the lower next queue where you are using a different algorithm, first come, first serve. Maybe this process is going to take considerably longer amount of time. So what you can do is that you can schedule it because it is a long process, a longer process, and we don't want it to block the shorter processes. So we put all the shorter processes, randomly shorter processes in Q0, Q1, and the longer one goes in that FCFS. So all of these will get first, these will get the chance, then these will the processes in this queue, and then in the lower queue, where all the processes are scheduled according to FCFS. So any questions regarding that example if you didn't understand? Yeah.
Essentially, the process just goes downward. It can never go upward.
It can go also upward, depending upon what are the details of your. This is just a particular example. Depending upon what are your criteria for moving down or up a process. So here is a more complete picture. So a specific multi-level feedback queue scheduler is defined by the following parameters. How many number of queues you have? In that example, we had 3. Okay. Scheduling algorithm for each queue. For the first queue there, we had time slicing using different quantum values. And for the last queue, we had FCFS. Method used to determine when to upgrade a process. So what was the method you were using for each queue? When to upgrade or downgrade or demote a process. So for the downgrading, we were saying if a process doesn't complete its execution in its quantum, we move it to the next queue. And even then, if it doesn't complete, then we move down it to the next queue, right? So in the same way, you can define a strategy or a criteria to move a process from lower queue or lower priority queue to the higher priority queue, okay? And then method used to determine which queue a process will enter when that process needs service. So here in that example, we assume that by default, a process enters first in the highest priority or first queue, right? Maybe you can define a different criteria. Maybe you can select a different queue depending upon the priority or depending upon maybe the bus time it needs and so on. Depending on any criteria, you can define, okay, where the newly arriving process will go to the first queue, second queue, third queue, and then how it will move among the queues. Okay. Any questions? No. Okay, if no questions, then let's have a 10-minute break, and after that we can.
Do what do you really do? Yeah, and I would mention without the so we're not actually we have to know that. But if we're down, it's very on me.
because so you do some stuff like they're I'm actually so art is weird like a lot of
Actually, would you mind I wouldn't use I was thinking we have a really nice
Okay, let's get back to the lecture. So remember when we were talking about threads or supporting threads at user level or kernel level, we also talked about how user level threads, irrespective of how threads are implemented, the support for threads are implemented. We also discussed about how user level threads are mapped to kernel level threads, right? Because the scheduling is always performed by the kernel and it schedules the kernel thread. It doesn't schedule the user level threads, right? Because kernel don't see the user level threads. So so until now, we were basically discussing about the scheduling a single threaded process, right? But now let's say we have a process which has multiple threads. Let's say I have a process which has 4 threads, right? And definitely when I'm talking about threads, this is like a user level process, right? But if these are like user level threads, they need to be, I'm just writing U and the user level threads, okay? So they need to be mapped to the kernel level thread. And we talked about different strategies which are used. And one of them was one-to-one, right? Which is used in Linux. So basically, which means that each user level thread is mapped to a kernel level thread. So if you have 4 user level threads, you have 4 kernel level threads, right? So basically, which means that kernel will be scheduling all these threads, and And as a result, what will happen is that at the kernel level, you have a thread table where you will have an entry for each one of these threads, right? Now assume that if we have a single core, right? So what will happen is that if the scheduler the kernel need to schedule one of these threads, so what will happen is that all of these threads will compete for this single core, right? So this basically, which means, and now let's say I extend the example. So I was considering only one process A, right? Let's say you have a process B. I don't want to draw again. So let's say you have process B and it also has 4 threads, and both those user level threads, and those 4 user level threads are mapped to 4 kernel level threads. So in total, if you have only 2 processes currently running in the system, in total you will have 8 threads, right? And if you have only one core, so you need to run those 8 threads on the single cores, which basically means that each thread will compete with all other threads in the system, right? So this is known as system competition scope, because each thread competes with all other threads in the system to get the chance to run on the code, right? And that is basically coming from the fact that each user level thread is mapped to a single kernel level, right? So each user level thread in effect competes with all other threads, correct? So this is known as system level, a system competition scope. On the other hand, remember we also, so this was like one-to-one mapping, right? We also had other types of mapping, and which one of them was many-to-one, right? So let's say if I simply so now let's say if I have again the same process, say with 4 user threads. So in many-to-one, what I do is that multiple user level threads are mapped to a single kernel level thread. So from which basically means that now if this user level thread, let's say I'm naming it as a thread 1, thread 2, thread 3, thread 4, which basically now means that if thread 1 want to execute or want to get the chance to run on the code, since the scheduling is done by the kernel at level of the kernel level thread, so it basically means that this T1 will compete with all other threads of the same process, right? And if you have another process B, and again I'm doing the same thing, you have 4 user level threads mapped to 1 kernel level thread. Sorry for this drawing. So these 4 threads will, each one of them will compete with everyone else to get mapped on this kernel level thread, and every one of these 4 threads will compete with other threads in the same process to get mapped on this kernel level thread. So this is known as your process competition scope. So each user level thread is competing with your siblings in the same process to get mapped to the kernel level thread, and then when this kernel level thread is mapped on the code, let's say this one gets the chance, so it is mapped to this one, and when this kernel level thread is mapped on the code, so basically now you are running, let's say, thread 5, 6. You are running thread 6 here, right? So there is like 2 levels of competition. One at the level of the process, then at the level of the system. This is right. Okay. So I'm not reading this slide because I have said the same thing. So actually, when you schedule in your operating system, for example, in Linux, when you schedule the threads for execution, you can specify that what kind of competition scope you need to set, you want to use. So basically in Linux, as I said, it always uses one-to-one, not many-to-one, one-to-one mapping, and most of the modern operating systems use this one-to-one. So basically it means that you can use or you can set the competition scope only to the system level, because each user level thread is mapped to a separate kernel level thread. So all threads every thread competes with all other threads in the system. Okay. So, and that is also the default one in the Linux. So basically, you don't need to do anything, but this is just like for your information. So you can use this pthread API, pthread attribute set scope, where you can remember if when we talked about pthread API in one of the previous lectures, we also talked about the attribute data structure. So you first define the variable of the pthread attribute type, and then you can initialize its entry, the entry of that data structure, such that you are now setting the scope to the system level. This is also default in the Linux, so you don't need to worry about it. And the other thing is that you can also set the scheduling policy for the threads. Like we have until covered, for example, first come, first serve, or short job first, SRTF or round robin, right? So you can specify the scheduling policy. Here, when you are saying scheduling other, this is also the default scheduling policy of the Linux, which is time sharing or time-based scheduling, time slicing. Okay, but you can, if you want, you can specify here that you want to do FIFO, which is a first come, first serve, another name of first come, first serve. Okay. Or for more detail, you can simply go and check the manual page of the pthread API, or you can simply Google for this and it will give you what are other scheduling policies options you have. Okay. Okay, any question here? Everything, I'm not walking you through the code because everything is same. You are simply here creating the threads. You are first setting their attributes. You are setting the policy. You are then creating the threads, and then you are waiting for all those threads to complete. And then your this is the function which is executed by the thread. Here, when you are creating the thread, you are saying execute this function. Remember, when we create the thread, we have to specify what code is to be executed by a particular thread. So we are saying runner, and runner is a dummy function. You can put anything here. Okay. Your question?
So the kernel thread is going to be scheduled as many times as we have user level threads on the core for all of them to run?
No. So let's take this example. So you have two kernel level threads. So the scheduling will be done at the level of the kernel. So which means that only either, let's say if you are single core, either this thread or this one get the chance at a given time. But I think if I get your answer correctly, you are saying that will it keep scheduling again and again until all the processes, all the user level threads get the chance and they have completed their execution, right? Yeah, then it is true. Then that will happen, yes. Okay, any other thing? Any other question? Yeah, go ahead.
Can two kernel level threads run at the same time?
Anyone who want to answer this question?
Yes.
No.
Okay, okay, let's first go with yes. You said yes, right?
If we have multiple cores.
Yes, you
have only one core you cannot.
you get the answer, right? Okay, so until now we were talking about scheduling single threaded process on a single core or a single CPU, right? Now we are going to ask a different question. We have multiple processes, and those processes can be single threaded or multi-threaded. And we want to schedule, and we don't have single core, we have multiple cores or multiple CPUs. So how this change the different questions related to scheduling policy, right? So one thing, like, it will become more complex because now you are introducing more questions into the picture. So first thing is that, remember we talked about different type of architectures in one of the previous lectures. I'm not going again through them, just naming them. Multi-core CPUs where you have single CPU on a single chip. Multi-core CPUs where you have on a single chip, a single CPU, but within each CPU you have multiple cores, right? Then you have multi-threaded cores. This is maybe new one. I will explain it. So, and okay, I'm just skipping it for now. Numerous systems where you have the basic idea was that you don't want to become the memory bus a bottleneck. So what you do is that for each CPU, you have one local memory. So if the process running on that CPU need to access the local memory, it doesn't need to compete with other processes running on other different cores or other CPUs it doesn't need to compete for this memory bus, okay? And heterogeneous multiprocessing is, one is like homogeneous. Homogeneous mean that you have multiple cores on a single chip and all those cores are identical to each other. Like identical mean like, let's say you have core A, B, and C and D, and all of them are pipelined and all of them have, let's say, 5-stage pipeline, okay? And all of them have same size of L1 cache. I don't know whether you guys are aware of this terminology or not because you have not taken architecture course, but I cannot teach you architecture here, okay? So the heterogeneous is that, again, you have, let's say, A, B, C, D, 4 cores on the same chip, but they are different in their detail of their microarchitecture. Maybe one of them has a pipeline with 5 stages, another has the pipeline with 10 stages. One has L1 of 4 kilobyte, another has L1 cache of, let's say, 16 kilobyte, right? One has maybe prefetcher, the other has no prefetcher, and so on, okay? So like they are different in their features, okay? So which basically means like which can affect the performance of a multiple core. For example, if you have normally, not always, but normally if you have a deeper pipeline, which with more stages, you can have the higher throughput, like which means you can complete more instructions in smaller amount of time, right? So, but we are not going in that direction, okay? So when you have multiple cores on a single on a single chip, so how to do then scheduling? The first, with the very, how to say, the abstract question or the top level, the higher level question is that can all the cores on the single chip are capable of running the processes or not? And this comes to the question, this like boils down to the point, because we know when we are running the user level processes, most of the user level processes also need the OS system calls for their execution. So the question is that are the cores on a chip allowed to execute any type of code or not? So basically you can divide code into 2 main categories, user level and the system level, right? So one approach is that we say, no, not all cores cannot execute all type of code. We have a master core, which is capable of executing system level functionalities like system level OS system calls. And all other cores, they are named as, like, let's say the slave cores, they can only execute the user level code. So one core is responsible only for interacting with the OS. Other cores, they can do only CPU, only the user level code, which doesn't involve any OS system calls, right? So this is known as asymmetric multiprocessing. And actually, if you remember, we have briefly touched on this in one of the previous lectures, right? However, this one is simple to implement because only one core can execute the OS code. So basically, which means that all other cores, they are simpler. But the problem here is that then there will be a lot of communication going between the master and the server cores, right? The other cases, which is now more prevalent and modern, which is used in all modern systems, is symmetric multiprocessing, where we say that if we have multiple cores in a single chip, all of the cores are capable of executing both CPU user level code and the OS level code. Okay, and we are going to focus on this one, symmetric multiprocessing. So let's say you have this architecture where you have multiple CPUs, or let's say multiple cores. I am using these two terms interchangeably, CPU and core. So basically, I mean that you have a hardware resource which can execute the code. So you have 3 CPUs, then each one of them have their own cache, and then you have the main memory. So your kernel sits in the main memory, and the kernel has a component which is named as scheduler. You have multiple processes in the residing in the memory P1 to P10, right? So now the question comes is that if you want to schedule these processes on these cores, how you are going to schedule them, right? So let's say all of them are ready. So all of these 10 processes are ready. How you are going to schedule them on these different cores or multiple cores, right? One option is that since what you can do is, again, we are using the process and thread interchangeably, okay? Because we are assuming one-to-one mapping. So one way you can do is that you can maintain a single ready queue for all the processes in the system. Whenever a process becomes ready, it goes to the same ready queue. But you have multiple cores, right? So now what you do is that you can, but if you want to schedule a process on a core, you always go to that ready queue and you get the process from the head of that queue and put it on the core. And if the next core is free, you would again go to that same queue, get the next process from the head of the queue, put it on the next core, and so on. Like, I'm just trying to simplify. Here, basically, what we are trying to focus is that what is the relationship between the ready queue and the cores, not the schedule. We are not right now yet focusing on the scheduling algorithm. We are basically focusing what should be the relationship between the ready queue and the number of multiple cores. Now, what is wrong with this approach? Okay, first, what is good with this approach? Simple to implement. You have a single queue, and for every time you need to assign a core to a ready process, you go always check the same ready queue. So you don't need to manage multiple queues. Okay, but what is wrong? Whenever you share some resource among multiple entities, what can happen? I have one book and 4 students want to read from the same book. What's going to happen? There will be contention, right? That at the same time, when student 1 want to read that book, maybe student 2 also want to read the same book, right? So what can happen here? There will be contention in the sense, let's say core 0 is going to get the process from the head of the queue, and at the same time, what happens that the core 1 also want to get the process from the head of the queue and run it on the, so there will be a race condition, right? So which means what we need to do is that we need to synchronize the accesses to the ready queue. So which basically mean that we can put the locks. So whenever the core 0 is empty and it wants to put some process running on itself, what it can do is it can get first the lock. When it gets the lock, it's mean now no one else can access the queue. It can get the process from the head and schedule it, run it on it, then release the lock. Now the head is updated, right? Now when core 1 wants to get, it will first request the lock. If it successfully gets the lock, then it can get the process from the head of the queue and run it on, or we can run it on the core 1. And then after like getting or retrieving the process from the head, you can release the lock and so on, right? So you can do the locking to solve the problem. But what is wrong with this locking method? Let's say you have one core and you have 64, sorry, you have one queue and you have 64 cores on the single chip. Every time you need to get a process to run on the core, you need to get the lock. And when I successfully get the lock, all other contenders who are requesting to get the lock, they must wait, which means that overall performance of the system slows down, because more you wait, more you are wasting the resources, right? So this is problem with having the single ready queue. Now to solve this problem, what we can do is that we can maintain a separate ready queue for each core, right? Now, all the ready processes which need to be run on the core 0, they will be waiting in the, let's say, queue 0. And all those which want to run or need to be run on the core 1, will be waiting in their own queue, right? So in this way, now you don't need, there is no contention, there is no need for locking, there is no drawback of, you don't, how to say, incur the overhead of locking, okay? However, there is another problem. There is no perfect world. What is the other problem? Maybe, like as shown in this example, there are 4 processes that want to run on core 0 and they are waiting in their ready queue. But this core 0 can run only one of them at a time, right? And core 1 has only 2 processes, and core 3, let's say, has only 3 processes waiting, which means that this core 0 is overloaded as compared to core 1, right? So the workload is not equally distributed among all the cores, correct? So, which means like after, let's say all of these threads are take the same amount of time to complete. It will become idle after completing 2 threads, and this will still be have to run. This will still have to run 2 more threads, and this will still have to run one more thread, right? So which means that now we need to do the load balancing across the cores. So we need to make, just like, remember what is that? What is the purpose of multi-threading? The purpose of multi-threading is that if you have single core, you want to keep it busy all the time. Remember we talked about that a process can have CPU burst and IO burst during its execution time, right? And we said, okay, one process or one thread has CPU burst and the other has IO thread, and it is waiting for the IO thread. We can like interleave such that we have continuous CPU burst on the same CPU. Same is the target we want to achieve here, that we want these cores to be busy all the time, okay? So, which means we need to balance the load. So definitely then there are some solutions about load balancing among the cores. So we are not going in that direction, what are the load balancing algorithms, but we were just trying to highlight the point that if you have multiple cores and you have multiple processes, you want to schedule them on multiple, there are multiple aspects of the problem which you need to consider. The problem is now as not simple as it was in case of a single core CPU, okay? So, I have already talked about multiple processor cores. Now there is another issue. Even if like, remember in the first slide or in another slide, we talked about multi-threaded, multi-core processors. What is that? So let's say you have this single core, core A, okay? And you are running a thread or a process to schedule a thread or process on it. Now, let's say this is the timeline for the execution of that thread which is running. Let's say thread 1 is running here, and this is the timeline for execution. Now, what will happen is that typically it will run and it will do some, it will execute some instructions. You remember when when instructions execute, even in that simple case, like I always give you this example of like, let's say C is equal to A plus B, right? So A and B is first going to be retrieved from somewhere. And that somewhere is the source of A and B is registers of the processor, right? Accessing registers is much easier, easier in the sense it is much faster as compared to accessing the data from memory, right? So now let's assume that you have these registers R1, R2, R3, and you have brought the data from memory. In memory, you had A, B, and C. So you put it A here, you put B here. Okay, so you have the value of A, let's say it was 1, and B here 2. So now you add it, and then you need to write. So here you are actually basically now doing addition. Okay, so you did the addition, and after that you need to put the value in C. But C is in memory. C is not yet brought into the R3, which means that you need to write this data down into the memory, or first bring this data into the register, and it will take time, right? So this will take time. So this, as a result, because you are accessing memory, so this will take time, and this is known as memory stall, MS. Okay. So which means that your CPU or your core has to wait for the data to arrive from the memory into the register, and when it is waiting, it is doing the thing useful. Okay. So what you can do is, so this was like execution timeline of thread 1, right? So what you can do is that when it is waiting, you can allow another thread 2. So this is like compute. So here it was compute. And this is memory stop. So you can allow another thread such that here it can perform its compute. Still you have single core. Still you have a single core. But first what you did is that you allow the thread 1 to run on it. But then when it's faced the memory stall, instead of wasting your time, you said, okay, I can allow thread 2 to execute on the same core, right? So what is thread? If you remember, we said thread is simply an execution, a sequence of instructions, right? So if you have this thread 1, you have thread 2, and you want to like execute them on the same core, you need to keep track of like where is the current instruction to be executed. So it should have its own program counter somewhere pointing here. Let's say PC1, PC2 pointing somewhere as some instruction. I don't know maybe here. So basically, which means that if you want to run 2 different threads on the same core, you need to have 2 different program counters to track where is the next instruction of each thread to be executed, right? Because they are independent different threads. Not only that, when you are executing them, just like I gave you an example here, if this here you are doing A plus B, here maybe you are doing Z plus F. Let me just like make a fake example. So you need to also, just like you put A and B in register R1 and R2, you need to put Z and X into some other registers. But you cannot put in R1 and R2 because it will overwrite, right? So which means that for this thread, you need to have own registers, not only thread-specific program counter, but also thread-specific register. However, when I say then what does it mean? If they have their own program counter, they have their own specific registers, then what does it mean that they are running on the same core? It means that they share the same pipeline, processor pipeline, and they also share the same caches for the core, right? But then within the same core, you have their own independent program counter and the registers, right? To track the execution or to support the execution of each one of them, right? So this is known as, so now what is happening here, you have a single core, but you have 2 threads supported on the single core. Because the single core maybe have separate 2 program counter registers, P1, I'm just like trying to make it easier to understand, and maybe you have 1 register file, RF1, you have 1 register file and you partition it, half of it to give to, okay, to 1 thread and the other half to another thread, RF2, register file 2, right? But still it is the same core. So it is single core, multi-threaded. And when you have multiple cores, it will become multi-core, multi-threaded, right? So, okay, the time is over. Can I just quickly read the same thing? Here you have the same 1 thread, you have compute cycle, you have memory cycle and memory stall cycle. So this is the execution. So what's happening? So this is the same thing what I said. You are trying to interleave them to avoid the wastage of the resources. And this is known as like multi-threaded, but then to achieve it, you have to have separate program counters and register file. Now, what will happen is that here is the example. So you have 1 single processor, it has 4 cores, and each core can support 2 different hardware threads. 2 different hardware threads because we are saying that each one of them have their own program counter and own registers. So in total, you have 8 hardware threads, right? But what happens is that from the operating system perspective, each hardware thread appears as a single CPU, logical CPU, not physical. Logically, it treats each thread as a single CPU, like CPU 0, CPU 1. So there are in total 8 logical CPUs. Why 8 logical CPUs? Because there are 8 hardware thread and each hardware thread runs independent of the other, right? Questions? Okay, then let's stop here.
Already done.